Hello, my name is Maria Satnik. I'm a graduate student at William & Mary. Today I will be talking about my poster that I've submitted for the 2022 JLab Users Group Meeting Student Poster Competition. And today I will be talking about the GRINCH Cherenkov detector as a part of SBS, which I've actively been a part of since 2018. The gas ring imaging Cherenkov detector, otherwise known as the GRINCH, is a heavy gas Cherenkov detector that is part of the Big Bite spectrometer in Hall A at Jefferson Lab. Its main use in the SBS spectrometer is to distinguish pions from electrons. The GRINCH was installed in spring 2021 and was filled with heavy gas in January 2022 and began taking electron data then. This presentation / talk is going to give an overview of the commissioning during this runtime and my participation in the GRINCH thereof and its preliminary performance results. A little bit of background on Cherenkov light. So when a particle travels through a medium at a velocity greater than the speed of light in that medium, it creates a Cherenkov light cone, which we can detect with photomultiplier tubes, also called PMTs. And those appear as a ring in the detector. Electrons will have a greater velocity than a pion at the same momentum due to the smaller mass of the electron. So when you have a medium, you can choose a medium with a certain index of refraction that the electrons will shrink off and the pions will not, up to a certain pion threshold. Here I have a diagram from Leo about how a Cherenkov light cone propagates. We have a particle traveling through, and we have the light cone propagating behind. So a little bit about the GRINCH design itself. The GRINCH consists of 510 29mm photomultiplier tubes that are set up in a honeycomb array. It consists of 4 highly reflective cylindrical mirrors and is filled with C4FO8 heavy gas. And its design was to have a 2.7 GeV per C pion threshold, so pions below that threshold are not going to make Cherenkov light. Here I have a couple pictures from the Agenda 4 simulations from the GRINCH technical report back in 2012. Here we see let's look at the top right one. So this is a picture from up above the detector. You have an electron coming through that's going to make a Cherenkov light cone. That light cone then gets reflected off of the mirror into the PMT array and will make little rings, which you can kind of see in the illustration in the bottom left as those 2 small rings. So the GRINCH was running during GMN. In January, like I said, we put heavy gas in the Cherenkov, or in the GRINCH, so that electrons were actually making light, Cherenkov light, and we were recording that data. So we can take the leading edge of the signal. So for a single PMT, every time that a signal comes in, the time is recorded between the trigger and when the PMT sees that signal, and that's put in the histogram, which we can see on the upper right. So naively, all of the flat would be background, and then that peak, that Gaussian, the peak in the center, would reflect real electron events that are coming in time with the trigger. So we can do a little bit of math, and looking at a couple runs from this time, there's about a 250 kilohertz background rate for each PMT, with the Gaussian of the real events sitting on top of that. So the width of that Gaussian is about 5 nanoseconds, which is sometimes called the timing resolution for a detector such as this. Doing a little bit of math, we know the background rate, and say we want to look at a 10 nanosecond window, that means that there is a 0.25% chance that there is going to be noise happening in the timing window that we want to look at. And that is often called the detector's occupancy, which is dependent on the window size that you're looking at. On here, I have some results on the left of taking all 510 PMTs, fitting that leading edge histogram with a Gaussian, plotting the mean of that Gaussian and plotting the sigma of that Gaussian, showing that we have about a 5 nanosecond sigma, or timing resolution is one way to call it. And we do see this pattern in the mean of possibly something because of the structure of the mirrors, or maybe because of the different, the 4 different data modules possibly causing some timing difference that needs to be investigated a little bit more. And the bottom right graph is just showing the rate, the calculated background rate, which we have a couple PMTs that are noisy and a couple PMTs that are dead. Cluster finding. So one of my big projects on the GRINCH has been implementing a cluster finding algorithm for the GRINCH for real electron data. So the algorithm that I created and implemented at the moment requires a hit of 3 or more neighboring PMTs to all be firing within a given time window. In these examples, I actually have a very large timing cut of 40 nanoseconds. So when things are ideal, we could actually get that down probably closer to 10 nanoseconds, or more in the order of the resolution, the timing resolution, which we determined was about 5 nanoseconds. So if we look at that middle one, that is a couple of examples of real electron events from data that happened in the GRINCH from the single event display program. So we have these nice little clusters of 5 to 7-ish PMTs that are representative of that light cone being made from that electron and reflecting off of the mirror into the PMTs. So if you look on the bottom left, that is a picture of what the PMT array looks like from inside the detector, and we have those little light catchers as well. So the light bounces off of the mirrors and into the PMTs. On the right is a heat map, or a 2D histogram of the calculated centers for all the clusters in this particular run. So I ran this particular run, I did cluster finding on it, I took the average of those cluster centers and I mapped it here. So we have this kind of funny sideways shape where it looks like there's a lot of events in the middle of the GRINCH. There's not a lot of events on the outside of the array. And we do have a little bit of this funny shape. One of the mirrors is known to be damaged, the bottom one, so it could possibly be a reflection of that. And we will be fixing that bottom mirror before the next run. Just a little bit about the GRINCH as a part of the spectrometer as a whole. So when in certain kinematic settings, it's going to be difficult to tell pions and electrons apart by momentum and energy alone, that we need the GRINCH to add information in of being able to tell those similar momentum pion and electrons apart. So on the bottom left is a little cartoon of the setup. So we have the particle coming in, interacts with the gems, which do tracking, interacts with the GRINCH, which is what I'm talking about, what does the particle ID. We have another gem for tracking, pre-shower for energy, hodoscope for timing, shower for energy. Well, they all kind of measure energy and momentum. And then here is a picture of GRINCH in the hall. And it is, I like to call it the big coffin in the center of the SBS spectrometer. So what are the next steps? So the data analysis and the calibration for the GRINCH is in moderately preliminary setup right now, and I'm still working on it. So one of the next steps would be for me to do is to calibrate those leading edges, because we have those really funny timing offsets between the 4 different modules that you can kind of see here in this 2D histogram. So we would like to fit all of the Gaussians, and then we would like to set them all to the same time so that we can make a very small, say like 5 or 10 nanosecond timing cut on the leading edge to be able to better identify when the GRINCH has an electron event. I also do not have any hodoscope or timing corrections in this data right now. So that would be the next thing to do. Is the hodoscope has an extremely accurate timing. So if we look at our timing relative to that, instead of relative to just the BB Cal trigger, we can narrow those peaks quite a bit. It would also be very helpful to incorporate particle tracking from the gems. to be able to see where about on the mirrors different light events are hitting, and maybe if the edges of a mirror are being hit with a light event and it's breaking up and we're losing something. So that's would be a next good step. And from that, once we clean up the data, look at tracking, look at timing, all those kinds of things, we should be able to get more accurate numerical representations of the running efficiency for the GRINCH, which would be more or less how often, when the rest of the spectrometers see a good electron, does the GRINCH see a good electron. All right, so some conclusions. So the GRINCH is a heavy gas Cherenkov detector in the SBS spectrometer in Hall A, and its main purpose is to distinguish between pions and electrons in scattering experiments. The GRINCH began taking data for electron events in January 2022 during the GMN experimental run. Many data analysis tools such as cluster finding have been developed and implemented and are still in the process of being improved. And data cooking and calibrations are still somewhat in the preliminary stages, but good things are yet to come and plan to come. A couple references. I briefly referenced Leo. I briefly referenced the GRINCH Detector, the GRINCH technical manual. I also have a couple pictures from Carlos that I have cited here. And I would like to give a special thanks to Scott Barkis, Todd Averett, Carlos, Bridget, Eric, and there's several others who have participated on the GRINCH over these several years. All right, well, thank you for listening and have a lovely day.